Very good afternoon. Firstly, I'd like to thank Manish and Aranyak for having me here. Today, I'm going to talk about bargaining and Maxmin fairness, and this is joint work with my advisor, Ashish, at Stanford. Before I tell you anything about the problem, I'm going to tell you what my overall research looks like, or at least a significant portion of it. And the broad goal is to do or like design mechanisms for decision making. There are several approaches to this problem. And the classical approach is one with social choice. And the key characteristic here is that agents express their preferences to a central authority or agency with no interaction between themselves. So you can think of, there's a bunch of alternatives, and agents just rank those alternatives and submit it to a central processing unit, and then they get something in return. And some of the work I've done here, I've done some stuff with knapsack voting for participatory budgeting. How many of you know what participatory budgeting is, or can guess what it is? It's essentially like the residents of a city voting on a bunch of items to decide how the government should spend the money. And so we have a nice platform actually which we use for online voting in real elections. It's called pbstanford.org. And the other thing is looking at ordinal social choice, but with cardinal guarantees. I won't describe it much more here. I'm happy to talk about it offline. The second approach, and this is a little less clear in my mind, but I'm going to mention it anyway because it's a nice in-between sort of category. Here, agents interact with the remaining voters in aggregate. Maybe with some sort of a market mechanism, maybe with real money or fake money or something of that sort. An example of this is combinatorial public projects. And the third category is what we're interested in today, and that is where you have protocols where agents interact. And here, the agents are talking to each other directly in some sort of round robin format or pairwise format or something. And an example of this is bargaining, and that's our topic for today. And the outline I'll follow is this. First, I'll describe what the bargaining model is, what the underlying outcome space is, and so on. And then the question is, what is the outcome we're looking for? And we'll be looking for Maxmin fairness. I'll define what that is in this case. And then I'll define what the mechanism design problem is exactly in our case. And then we'll build up the mechanism in two steps. In the first step, I'll simplify the problem a little bit to that of just choosing one of two outcomes. It's sort of a binary selection problem. And we'll use that simple mechanism to build a much more complicated thing, which solves the problem that we have. Okay, so let's start with the model. So the standard model of the bargaining problem is very simple. You have n agents, and then a space of outcomes in Rn. And if you pick a point here, think of each component as the utility of the corresponding agent for that outcome. You also need to define an additional thing here, which is the disagreement point. And a disagreement point in any bargaining process is the result of a complete breakdown. so here, this is like a minimum guarantee. Like, if we imagine the people in this room are bargaining, then anybody can walk out and then say, I don't care what happens, and the mechanism designer in that case just implements D. So it's sort of like an exit option that exists. And this is mainly sort of as a relative reference point of what you're doing. And so based on where the disagreement point is, we suitably modify our initial space of outcomes to make sure that we're only considering individually rational outcomes.
Suppose you don't modify it, presumably whatever protocol it is will still
work. You need like additional bells and whistles. So
it's not just automatic.
Okay. Yeah. Things can, like, you have to like take care of it in the mechanism. Okay. So you have like an additional round where, like, so on and so forth. Okay, so the designer here does not know what the outcome space is, and just knows the disagreement outcome. When I say he doesn't know the outcome space, I mean, of course, like there could be some like abstract definition of what the outcome space is, like the set of all budgets or something, or like different ways of cutting a cake and so on. But what I mean essentially is that he has no idea of like the preferences or the utilities of those things. But a key assumption here is, and this is primarily a sort of like convexifying what the power of the designer is, that the designer has, so if you give the designer two outcomes, the designer can create all convex combinations of those outcomes.
What does that mean?
It means that it's like saying like I'm the designer, let's say, and I have no idea what your preference space is. You come up with some outcome, some abstract thing X, and Aranyak says Y. Then I can, sort of figure out how much you like, half X plus half Y or something like that, as compared to X, that sort of thing.
So they're thinking of outcomes as restaurants. If people want to go choose where to have dinner.
Then a randomized choice between the two. So that's one way of doing it, is to allow, if your inherent like space is very discrete, then you have to allow lotteries to make it convex. And sometimes it's also just possible just structurally, like I mentioned, with budgets and cakes and so on. Okay, so the next question is, okay, like I prefaced the model saying, the agent does not, the designer does not know anything about the outcome space. But the first thing we have to answer is, even if we knew what the space is, what is a good outcome? And any function that maps a space and a disagreement point to some outcome in that space is called a bargaining solution. And so usually when there's a question, what is good, people start defining axioms. There are lots of ways of combining and stating these axioms. I'm just going to state like two axioms that are almost universally enforced. One is Pareto optimality. And the reason you want this to hold is because something that's not Pareto optimal always, in at least in a layman's sense, allows room for further bargaining. And then you want your solution to be scale invariant with respect to each agent. So theoretically, if Manish just scales up his values, that shouldn't affect how the solution is being chosen. So So just using that axiom, we apply a normalization to S, and then we say for each agent, if you picked her favorite outcome, her utility is 1. And we also normalize the disagreement outcome to 0 for everybody else. So just placing the disagreement outcome at the origin and translating everything and normalizing.
So it is always a point, right? You cannot have a disagreement outcome where any of the players have a utility. I mean, is D a point or could it be a space is what I'm thinking.
It's a point because it has to be clear what's going to happen when disagreement happens. So if you walk out the door, like somebody should be able to say this is the outcome. It could be randomized over a collection of outcomes, but essentially something specific.
What's the role of this D? Like, do you need it? Like, suppose there is no fallback, like no D. Are there any hardness results, or like what breaks down?
No, it's just I think you need to do something when things break down. So you can either do D, or you can say, at that point I'm going to invoke a random dictator and end things. So it's some endpoint that you need.
Or you can just define it as you'll get everybody gets zero utility. That's basically what this is.
Yeah. But this is like just a formal model. So you have to be like, okay, what is it exactly in the space, right? So that's D. So it's also like a visual cue, like over when we talk about the mechanism and so on. Any other questions? Okay. So as you would guess, many solutions have been axiomatically characterized, but we won't get into those definitions in this talk. We'll only define things in a utilitarian sense. For example, the Nash bargaining solution is the maximizer of the product of the utilities. There are many other solutions. The Kalais-Morodinsky, which maximizes the minimum guy, the relative utilitarian, which maximizes the sum of utilities and so on. But the commonality here is that all these solutions involve maximizing convex functions, and the implementation of such solutions have been studied extensively. And the point of studying the Maxmin is that it doesn't fall into this category. And that's in that sense, that's the question we're answering here. And these mechanisms are known to be relatively simple. And
Maxmin the same as
What?
Maxmin?
No. Maxmin is a sort of when I say Maxmin, in fairness, I mean the lexicographical version of it, where you maximize the minimum guy, and then with respect to that, maximize the next guy, and so on. This is just one step, sort of the Rawlsian notion. Right. So what is the Maxmin fair solution? So the Maxmin fair solution is that outcome, S star, which lexicographically dominates every other outcome in S. Is everybody familiar with this, or should I define it? Everyone's good. Okay. So just remember this symbol because I'll be using it over and over again. Okay. Right. So if your outcome space is compact and convex, this solution exists and is unique. And as it's pretty clear, it's not directly obtained by maximizing a convex function. Of course, there's some way of defining it as maximizer of a limit and so on, but that's not really useful here. Okay. So we looked at the model and we looked at what we want. Before we go ahead, I'm quickly going to describe a combinatorial property of the Maxmin fair solution, which is pretty interesting, I think. And like sort of the whole mechanism hinges on this property of the Maxmin fair solution. So this property is called disagreement dominance, and it's a relation between any two vectors in the outcome space. So first, define the disagreement projection by X onto Y as saying you retain those elements in X which are smaller than the corresponding elements in Y, and if not, you just make them one. So we call this disagreement because imagine like taking these two like utility outcomes. You're essentially saying, like split the agents into two groups, one that prefers X, one that prefers Y, and then you retain the utilities of those guys in X who prefer Y, and vice versa. The disagreement dominance relation is defined as follows. A vector X disagreement dominates Y if pi xy lexicographically dominates pi yx. So in this case, this is just an example. I don't know why the color is bugged out. Right. So ignore the colors here. These bugged out. But so if this was A and this was B, then for the first three guys, they prefer B or A. The second, the next two guys, the fourth and fifth guys, prefer A or B. And so these are the projections. And so you create these projections and then just look at the lexicographic relation between the two. Okay.
So it's not just about the number of ones, right?
Yeah, it's that whole vector. Sometimes the one is like pivotal in deciding.
But sometimes it's not either.
Sometimes it's not either, yeah. Okay, so what we prove is that if you take the Maxmin fair outcome and any other outcome, then the Maxmin fair solution strictly disagreement dominates the other solution. And this is true, of course, for any other solution. I won't get into the proof here. It'll take me like 15-20 minutes to get through the proof. But what I will say is this: it's not just equivalent to lexicographical ordering. So it could be the case that you have so if a vector A is lexicographically better than B, it does not directly imply that it strictly disagreement dominates B. And so this is a very special property of the Maxmin fair solution alone.
When you're comparing lexicographically, do you first need to sort the numbers, right?
Yes.
Yes. And here they're ordered by the players, right? Player 1, player 2, like.
Yeah, here, yes. But to compare like these two, you have to order them.
Oh, you do.
Yeah, I mean, if you're comparing them lexicographically, yes, you would have to order them. But the definition makes sense. Okay. Yeah.
Using the Maxmin fair, a star disagreement dominates every other solution.
Yes.
If you have something that disagreement dominates every other solution, is it Maxmin fair? Does that go both ways? I understand that there's a one-way implication for a pair, A and B.
Yeah.
If you have A versus everything else,
then
is that if you only have?
I don't think so. We don't really need it, so I didn't really prove it, but that's my feeling is it's not. Okay. It's a good question. Okay. So now let's like actually define the problem. So when we say implementing a bargaining solution, this is what we mean. So can we design a mechanism or a game form with non-cooperative agents such that the desired solution is the only subgame perfect equilibrium? And here, like I said before, the designer does not know the utilities of the agents. The agents have complete information about the preferences of other agents. And we're looking for subgame perfect equilibrium here because bargaining is, generally considered a back and forth process. And, you have offers, threats, counter offers, and so on. And so you usually want to have a repeated game. You're almost forced to have, in some sense, a repeated game. And so this is the solution concept of choice. And like we talked about, the desired solution here is the Maxmin solution.
In non-statistic case, it's actually easy to find the Maxmin point?
Yes, at least for like convex spaces, it is.
And that's through some combinatorial.
No, I think there are ways of just doing it like by repeated like linear programs. So you somehow find the minimum guy, and using that you solve another program, and so on and so forth. I think you can.
And just to be clear, you could ask for just a Nash equilibrium. Like you could have defined the whole thing saying that, I'm going to implement that algorithm you talked about, and you just give me all your preferences, and I'll implement it, and that'll be the final answer.
Yeah.
Then you could have formulated this as a regular one-shot Nash equilibrium as well.
Yes, but then the problem is once you bring in Nash equilibria, it almost automatically brings in millions of meaningless equilibria. Right. So basically, anything where someone says like, I'm going to present you some option, and if you don't do that, I'm just going to walk out, right? Those sort of things like come in. Okay, so this is the problem. And now how do we actually solve it? So firstly, like what's known already? Like I mentioned before, there's a simple game form which implements solutions that maximize convex functions. But our problem is outside this domain. And now we come to a critical assumption that we need, and this goes back to your question earlier. It's related to it. So remember that we normalize D to be all the zeros vector. I'm going to make an assumption on the outcome space as follows, and I'm going to call it the veto assumption, which is that for each agent I, if you look at her best outcome, she gets 1 and everybody else gets 0. And the implementation question without this assumption is also pretty interesting, but not much has happened there. I can talk about it later. But this is basically saying that everybody has the option of grabbing like the entire surplus. This is of course true in, if you have like cake cutting or something. Of course, like you can grab the whole cake and you get maximum utility and everybody else gets nothing. But that we don't need all that structure of cake cutting and so on. This is the minimum structure that we need, and you can show that this is like strictly more general than any of like the canonical problems that have been studied, where like this assumption might arise.
Does it say that this is one of the best assumptions, or does it say this is the unique best outcome?
This is the unique best outcome.
Okay.
What is the vector of all ones? Is that not in S at all? Or
that is not in S, no.
And even like 0.1001 is also not.
No.
But in a cake cutting setting, if everybody gets the pie they like, then wouldn't that be all ones?
They want the whole cake.
Oh, they want.
Yeah, they want the whole cake. Yeah, they want the whole cake.
And eat it too.
So in some sense, there is some amount of externality, but the externality is like not like they're not super strong synergy also. So we agree, like we both want the same things, but we don't want the same outcomes in some sense. So like there's some balance between the two.
I don't get it. Why is it called a veto assumption? Like, what is the veto power coming in?
I mean, this assumption doesn't have a name in literature. This is something just I came up with on the fly. It's just like saying,
Is this same as implementing D?
Sorry?
Is this equivalent to implementing D?
This is not equivalent to implementing D. D is just like everybody getting nothing, for example. So D is somebody like walking out of the process. This Li star is what is your favorite thing among all the things that we could actually do.
But is this realizable?
Yeah, it is realizable, yes.
Oh, it is?
Yeah. It's part of the outcome space. There is some point where you're the most, you're happiest and everybody else is, only as good as, walking out, basically.
Right.
So that's the assumption. And this assumption has like always been used, except for one piece of work, which does not, and I'll talk about it later a little bit. Okay. So we'll first look at a simpler problem, which is just given S star and some other S, can we design a game which implements S star as the unique subgame perfect equilibrium? And what we designed for this question, we'll call the knockout mechanism, which is sort of like a pairwise decision between these two outcomes. And in fact, this mechanism will answer or will guarantee something more general, which is that whenever you have two outcomes and one disagreement dominates the other, you can use this mechanism to implement the better one. So in sort of this is the simple problem is the easiest way to visualize this, but we're actually shooting for something like stronger. And then we use this knockout mechanism, and then we build a whole binary tree of games. And then once we've designed that thing, if you look at the overall mechanism, then that will have the Maxmin fair solution as the unique subgame perfect equilibrium. Okay, so let's define the knockout mechanism. So round 0, so we have these two outcomes, S star and S. In round 0, each player in turn chooses one of these 2 points. And then in round 1, each player bids a vector, an n-dimensional vector. And you can roughly think of these vectors as the utilities that you're promising people that disagree with you. So imagine you walk into this mechanism and you prefer S, then your bid, these numbers are going to correspond to. Of course, there can be anything as far as the game is concerned, and that's why we don't need to know what the utilities are. But in terms of tying it to the equilibrium, this is what it'll mean. So it's useful to have this connection in mind, which is I'm going to specify ones for everybody that agrees with me in my bid. and then I'm going to specify their utility in my outcome as their component in the bid. Does that make sense?
And that would be lower than what they expect to get from the other side.
Exactly. So that's where like I'll channel disagreement dominance. So we're setting it up so that disagreement dominance can play a role. And now players are ordered such that these bids. So you order the bids lexicographically in any way.
So there's no strategic behavior here, right?
No, there is. So this will be no. Why not?
In the sense, if I'm going to take your utility and use it to set up this vector, eventually that will be used in this dominance.
Yeah. No, I'm saying that's the connection I want to keep in mind. So there's no restriction on what your bid can be, right? So bid can be any like n numbers in 0, 1. But I'm like talking about this connection because the game is set up in such a way that the strategy, the equilibrium of the games is set up in such a way based on disagreement dominance that in equilibrium this is what is going to happen.
Okay.
So just to visualize what those bids mean. Right. So players are ordered based on these bids lexicographically, and the one with the best is defined to be the winner. So now I'll skip round 2 to round n for now. I'll describe it in a brief moment. But just think of these intermediate rounds as where you go through the players and each player either accepts or rejects and something else happens. But at the end of this whole thing, if everyone accepts, then what the winner proposed in round 0 is chosen as the outcome. Is that clear?
So just to be clear, the proposal happens just once, or every round is going to happen when you fill in the details? Are these...
There will be some recursion, but
okay, and there could possibly some reordering of the.
Yes.
But
yes.
L1 is still from the first round.
No, it
keeps
changing. It'll change recursively.
Okay.
But this is just like one run of this thing. Right. So in each case, so in every execution, when I say L1, it means the guy who wins the bid in that round of processing. So it'll become clear in just a second. So this round n-i is where player I can either accept L1, which is the winning or the proposal of the winning person in that round, or you can reject, right? But what happens when this reject is chosen depends on what this guy what player I was being promised in that round. So it depends on whether P1, comma I is less than 1 or equal to 1. So P1, comma I is the component corresponding to player I in the winning bid that's being looked at right now. So in the case where P1, comma I is less than 1, what happens is you define this outcome, which is mixing between I's favorite outcome and the disagreement point, and based on what the value of P1, comma I was. Right, so you define this lottery, and you choose that is the outcome, and the game terminates at that point. So if someone exercises the option of reject in whatever round of the game, right? This is what happens when the game terminates. But if P1 comma I was equal to 1, then what happens is player 1, or rather the winner of in that round, is eliminated from the game, just thrown out, and the game recurses to round 0 with just the other agents. So implicit here is that the agent can sort of eliminate this guy and not talk to him ever again, or rather, the designer cannot talk to this person ever again.
So that person will get 0.
Not necessarily.
Oh, they're just not participating in the game, but they might eventually
Yeah.
get a good outcome.
Yeah, it might.
Depending on what happens.
Yeah. But so this is a game. So it's sort of like a recursive definition of what's going on. Any questions?
So just to make sure we understand it.
Yeah.
So if you're using if the bid is the dominance thing for the other guy, then I really should not be rejecting with the equal to 1 branch, because I is kind of being told that you get what you proposed.
Are you trying to understand why this is like
Yeah, I guess so.
we'll do that. Like,
Alright, sure.
like procedurally, if you understand it, we can actually do that. That's my next slide, actually. So, okay. So why does this work, right? So that's the next question. So before we do that, this is what, so imagine player I is rejecting in some round, right? Then in the first case, the utility of this player is just P1I. Right, because 1 in the first outcome, 0 in the second outcome, and it's just P1I. So, and the second case, the utility of player I is given by the equilibrium of the smaller game. And for the purposes of this talk, let's just make that inductive assumption and say, like, for all smaller games, we know that the statement of equilibrium holds.
Sorry, I didn't follow the first part. So when P1I is less than 1, and Y is, so the D is 0, I get that.
D is 0.
And what is Li star?
Li star is this, right? Like I's favorite outcome, which is where I gets a utility of 1.
So you could always have just written P1I over here instead of the big parentheses. It's just literally the same.
Yeah, literally the same. But this goes to your earlier question, which is, like, what if you didn't like throw out the points which are not individually rational, right? Then how do I? If you ask for someone's favorite point, they could tell you anything. So then you'd like add another mechanism here to make sure that it's individually rational. So that's why we write it this way. So like the Li star would be the outcome of some other like smaller game you play to choose your favorite individually rational point. Okay. So let's look at a couple of cases to intuitively tell you why this works. So let's go with the assumption that the player 1 who's winning the bid strictly prefers S star over S, in the sense that he's on the right side of the world, right? And not on the dark side, and bids P1, which is the projection of S star on S. So now assume there's some player I who strictly prefers S over S star. He's on the wrong side of this binary. Then because of the bit being the projection, P1 comma I is equal to
S star I.
It should be S star I, sorry. Yeah, it should be S star I. Yeah, it should be S star I. So now, right. So now, if my question is there an incentive for I to reject? So in the case, so of course, if p1 comma I is less than 1, then the utility of this player is, this again should be si star, but this player I can just get si star by accepting. So there's no benefit to reject. And if, sorry, what happened here? Right. And like this case doesn't happen here, the p1 comma I equals 1. We are leaving that out because I'm only looking at the strict preference here. So v equal to 1 in this case would be indifference between the two outcomes. And so it doesn't really matter in this case. So this is a case I think that you were hinting at earlier, right?
Yeah.
Right. So the other thing, so this is saying that if the player on the right side can just bid the projection and nobody would want to reject. So the only thing the other person, like a person on the other side might want to do is try to outbid this guy. So the next case to look at is like, does the outbidding help? So now assume player 1 is on the wrong side, prefers S over S star, and then bids something more than the projection of S star. And that is required for overbidding because you have the other guy bidding the projection of S star over S, right? And so this, at the very least, this must be true if you want to overbid that guy, right? So now, like, there must exist a player I that strictly prefers S star over S, such that P1 comma I is greater than Si. So to make P1 better than this projection, you have to increase somebody's, at least one person's value. If you increase someone who's on the same side as you, then they're just going to reject and walk out, right? So if now you're looking at like, so then you're forced to increase someone on the other side. And that's what this is saying. And now, so player I, if player I accepts, then her utility is Si, right? Because the winner prefers S. So now these two cases are possible. Let's look at the first case where P1 comma I is less than 1. So in this case, the utility of this player is again this lottery, right? And this is P1 comma I, and that is greater than Si. So player obviously rejects. The second case is here it's possible, the P1 comma I equal to 1, and this is where the induction happens. So now claim inductively that the equilibrium outcome of the smaller game is also S star. Because you're throwing out someone who prefers S over S star. So S star is still better when you go to a smaller game among the remaining agents. And player I does not benefit by rejecting because Si star, you're kicking out some guy who's on the other side. And then so you benefit by going to the smaller game because you're eliminating a guy who's against you. So you prefer the smaller game. And therefore this, so effectively, like agents that prefer S over S star cannot outbid those that prefer S star over S. And so the rejection does not happen. Any questions?
There's a lemma here about Maxmin that when you eliminate someone who doesn't.
Yeah, the lemma can be directly applied to disagreement dominance, actually.
Okay.
So if there's something that if X disagreement dominates Y, and then you eliminate a person that prefers Y or X, then among the remaining people, X will still disagreement dominate Y. So So in effect, like we haven't used any property of the Maxmin yet. We're only saying like we have this mechanism which works when one outcome disagreement dominates the other outcome. So now we are going to use this mechanism to build up the whole game, and we build that up as a binary tree. So for the ease of definition, assume that the number of agents is strictly a power of 2. I mean, this can be defined otherwise too, but it's messy. Now define a binary game tree of log n depth. So at each stage, at each level in this tree, like so let's start with this source node. Like the source node, let's first assign groups of players to each of these nodes. So who's going to be playing in these games? So each of these nodes represents a game. So the source node, all the end players play, and then they're evenly split between its daughter nodes, and so on. And then you finally reach the leaf nodes, then you have just single agent assigned to each leaf node. So the game starts as follows. Like each player chooses an outcome, any outcome that they prefer. Call that PI. You label the leaf nodes with these outcomes. And the outcome of each node is recursively defined as the knockout mechanism applied to its daughter nodes, with the set of agents that have been assigned to that node. So if you look at a snapshot, let's say this was the daughter node of the source node. So here, the agents are n over 2 plus 1 to n. Then, so the outcome of this is recursively defined to be the knockout mechanism with these players involved and the outcomes of its two daughter nodes. And this is the final theorem. For the overall mechanism, the Maxmin fair solution is a unique subgame perfect outcome. I can briefly mention some intuition as to why the outer mechanism works. So now if you look at this, we know that in any knockout mechanism, if you have one outcome disagreement dominating the other, then that outcome wins, right? So now imagine that everybody chooses the Maxmin fair solution in the first round. And so you put all the Maxmin fair solution in all of these bottom leaf nodes. And let's just prove that this is an equilibrium for now, right? So imagine like somebody deviates. That's not going to help because they're going to lose in every contest that happens. And you can also show that this is the only equilibrium possible. It's not too hard. So I guess it's 5 minutes left, so I'll just conclude. So what did we do? We developed a mechanism for implementing the Maxmin fair solution. We looked at some cool combinatorial properties of the Maxmin fair solution. Like sort of looked at like this interesting nature of offers and threats and counter offers, which is sort of pitting groups that disagree against each other effectively. So one direct open question is, can the beta assumption be relaxed, or is it impossible? So my intuition, I only have intuition at this point, which is that it's not possible for Maxmin fairness, and it's already been done for like Nash welfare, and the reason being that like Maxmin fairness is a much more stringent concept. We can talk about this more offline. More generally, can we implement bargaining or social choice solutions that we like in some complex or simple, depending on what you prefer, decision spaces, using quote unquote more practical, simple protocols? Is there some kind of trade-off between like how complex your mechanism is and what the quality of the solution that you get? Thanks. I'll stop there.